So, when we discussed diagonal matrices, we observed that given a diagonal matrix A, if we consider the corresponding linear transformation LA, then LA dilates each of the vectors in the coordinate basis, in the standard basis, and it dilates it by the corresponding value in the diagonal. So, in this video we will explore this phenomenon in much greater detail in much greater depth for an arbitrary linear transformation from a vector space to itself. So, let us begin by considering a linear operator T on a vector space V. So, let T from V to itself be a linear operator on V. So, recall that a linear operator is just a linear operator on V is just a linear transformation from V to itself, that is T is a linear transformation from V to itself. So, for example, T being the identity map is the simplest example. So, for example, consider T equal to the identity map of V, then IV of V is equal to V for all V in capital V. Next simple example will be a multiple of lambda IV. So, this is one example. Let us consider another example. Now, let T be equal to lambda times IV, then TV is equal to lambda IV on V acting on V, which is equal to lambda times V. So, notice that our first example wherein the linear operator is the identity map, it dilates the vector space, every vector in the vector space by 1, or in other words it leaves it fixed. And the second example, every vector is dilated by lambda. So, if we consider an arbitrary linear transformation, this need not be the case, it need not dilate every vector. However, there are some special vectors in the vector space which might get dilated by a given linear transformation, and such vectors have a special name, they are called the eigenvectors. So, let me now give a definition. So, this is the definition of an eigenvector. So, let T from V to itself be a linear operator on V, or a linear transformation from V to itself. We say that a non-zero vector, notice that we are imposing a condition of the vector being non-zero. A non-zero vector V in capital V is an eigenvector of T if TV is equal to lambda V for some scalar lambda. So, if the vector V is getting dilated by some lambda, then V is said to be an eigenvector, provided V is not the 0 vector. The scalar lambda is called the eigenvalue corresponding to V, is called the, so let me just underline this, eigenvector of T, and this is called the eigenvalue corresponding to the eigenvector V. So, we have defined two objects here. One is the notion of an eigenvector, which is basically a non-zero vector in the given vector space, which is dilated by our linear operator, and the second one is the eigenvalue, which is the degree to which it is getting dilated, or in other words it is the scalar lambda such that Tv is equal to lambda times V. So, let us look at a few examples. So, maybe a good example would be, let us consider some simple example, say from R2 to itself. Let T be a map given by T of say x y is equal to 2x and 3y. So, we have already seen some examples here, we will come back to that maybe, but let us just focus on this particular example. T of x y is 2x comma 3y. If you notice, the coordinate bases are eigenvectors. So, let V1 be equal to 1 0, then T V1 is equal to T of 1 0, which is 2 comma 0, which is equal to 2 times V1. Similarly, if V2 is equal to 0 comma 1, then T V2 is equal to 0 comma 3, which is 3 times 0 comma 1, which is equal to 3 V2. So, the coordinate bases here are eigenvectors. So, the standard bases are examples of eigenvectors. If you will observe carefully, T is a linear map, right? There are plenty of examples of eigenvectors. Any vector, in fact, any vector of the type a comma 0 is an eigenvector of T. In fact, any vector of the type a comma 0 is an eigenvector of T with eigenvalue 2. Also notice that not every vector is an eigenvector of T. So, 1 comma 1 for example is not an eigenvector of T. Okay, so we have spent. So, why is a comma 0 an eigenvector? So, let me just put it in square brackets why this is the case. T of a comma 0, this is just 2a comma 0, which is just 2 times a comma 0, that is all. And why is 1 comma 1 not an eigenvector? T of 1 comma 1 is 2 times 1 2 and 3 times 1 3. So, it is 2 3, which is not a scalar multiple of 1 comma 1. Okay. Let us look at more examples. Let me put numbers. This is example 2. If T is the identity map, that is the first example maybe we should have considered, then every vector is an eigen. Every non-zero vector, notice that the definition of an eigenvector we have imposed this condition. Every non-zero vector is an eigenvector. With eigenvalue 1. Similarly, with the dilation lambda times IV, the eigenvalue there will just turn out to be lambda. Okay. So, every vector, another example, every vector in the null space of our given linear transformation T, which is if T from V to V is not injective, what happens? Then the null space of T has non-zero vectors. Let V be in n of T, the null space of T, or maybe let me write null of T, so that there is no confusion, such that V is not equal to the 0 vector. So, the 0 here is the 0 vector. And what does T do to our V? Then TV is equal to 0, the 0 vector of V, but that is nothing but the scalar 0 times our vector V. So, again it is your job to keep track of which 0 is where. So, this 0 is in the vector space V, this 0 is in the real numbers, it is a scalar. Okay. So, that means hence V, which is a non-zero vector, is hence an eigenvector, hence V is an eigenvector. And what is the corresponding eigenvalue? Eigenvector with eigenvalue 0. We have only demanded that the eigenvector should be non-zero. We have not demanded that the eigenvalue cannot be the zero scalar. We have not demanded that at all. So, yeah, so V is an eigenvector with eigenvalue 0. So, maybe a good exercise to think over would be to show that a vector or linear transformation is invertible if all eigenvalues are non-zero. Okay, let us look at more examples. So, next would be maybe example 4, I think. Yeah, example 4. So, consider this linear map. Let T be the map from R2 to R2, which is given by a reflection along a line. So, let me just draw it for you. Suppose this is our Cartesian coordinates. So, let this be 4 and let this be 3. So, this is our 4 comma 3, and let us look at the line joining the points. So, just first draw the line and then mark the point. This is our point 4 comma 3, and let us look at the reflection along this particular line which is joining 0 and 4 3. So, any point here is mapped to a point corresponding point here. So, in particular let us look at this line. So, I should not draw it like this. So, 4 3 3 minus 4 would be a perpendicular. So, this will come like this. This point will just turn out to be 3 minus 4, right. So, this is perpendicular. And what will T do to 4 3? Notice that if V1 is equal to 4 comma 3, then TV1, if you reflect the vector 4 3 along the line joining 0 to 4 3, it does not do anything to it, it just fixes it, right. So, this is equal to our V1. What about the vector say V2? So, let V2 be the perpendicular vector which is 3 minus 4. Then if you reflect it, it will go to the other direction. The other direction it will just be minus 3 4, right. Then TV2 is equal to minus 3 4, which is equal to minus of 3 comma minus 4, which is minus of V2. So, V1 and V2 then, so this let T be the reflection along L, where L is the line joining, where L is the line joining 0 0 and 4 comma 3. Okay. So, then T has eigenvectors V1 and V2. Notice that V1 and V2 both are non-zero, has eigenvectors V1 with eigenvalue 1 and V2 with eigenvalue minus 1. All right. So, let us come back to this example later. We will revisit this example. So, good example to have at the back of your mind while studying eigenvalues and eigenvectors. So, next, so we have defined what an eigenvector and an eigenvalue is for a linear transformation. So, linear transformations and matrices are very closely related, and you would like to define a corresponding or similar notion for matrices as well. So, let us do that next. Right. So, we do not consider 0 to be the 0 vector to be the eigenvector. Always keep that in mind, because in the definition itself we are incorporating that an eigenvector should be a non-zero vector, because there is no eigenvalue which can be associated to the 0 vector. Every scalar will turn out to be an eigenvalue, and we do not want that. Alright, so let us now look at what is meant by the notion of an eigenvector and eigenvalue for a matrix, for an n cross n matrix. So, let us start with an n cross n matrix. Let A be an n cross n matrix with real entries, of course. We say that a vector V in Rn is an eigenvalue of A with eigenvector of A with eigenvalue lambda if V is an eigenvector of the linear transformation LA with eigenvalue lambda. So, if V is an eigenvector of LA with eigenvalue lambda. So, for all practical purposes, we do not distinguish between the matrix A and the linear operator LA. Oh yes, I should probably introduce one more example, which is something which you have already seen. Let us consider a matrix. Okay, so this is good. At a good place, we will be looking at this example. So, let A be a diagonal matrix, say A1 to AN. Then my claim is that each of the eigenvectors of A, or each of the standard basis vectors, is an eigenvector of A. Then EI, let us just see what LA does to EI. Then my claim is then EI is an eigenvector of A. So, we should check that it is an eigenvector of LA, right. So, LAEI, if you notice, this is just AEI, which is equal to, we have already done this is going to be AI times EI. So, yes, it is indeed the eigenvector, indeed an eigenvector of A with, so hence EI is an eigenvector of LA with eigenvalue AI. Okay, next let's give ourselves a definition of what is meant by the eigenspace corresponding to lambda. So, definition of an eigenspace. So, let me write it down. Definition of an eigenspace. So, we have already seen what an eigenvector is and what an eigenvalue is. Let us look at what an eigenspace is. So, let T from V to itself be a linear operator. So, I will slowly start using this term more frequently, operator on V. That means it is a linear transformation from V to itself. Then the eigenspace of a scalar lambda is the set of all vectors such that TV is equal to lambda v. So, notice that every eigenvector of T with eigenvalue lambda is in the eigenspace of lambda apart from 0. 0 is obviously there, but every eigenvector corresponding to the eigenvalue lambda or every eigenvector which has eigenvalue lambda will also be in the eigenspace of T. So, let us try to see more about the eigenspace of lambda, say for example. So, if lambda is a scalar, so for lambda in R, let us see what it means to say that Tv is equal to lambda v. Tv is equal to lambda v can be rewritten as this is if and only if Tv is equal to lambda iv v, right, and by the operation of linear transformations, the vector addition of linear transformations, this is if and only if T minus lambda iv of v is equal to 0. So, i.e. this is if and only if v belongs to the null space of T minus lambda iv. So, v is hence v is in the eigenspace of lambda. So, rather eigenspace of lambda is just the null space. So, let me write it more in a more refined manner. The eigenspace of lambda is the null space of T minus lambda I. T minus lambda iv. So, in particular the eigenspace of lambda is a subspace, which is a subspace of V. So, lambda is an eigenvalue if there is at least one non-zero vector in the null space of T minus lambda iv, right. So, also observe that lambda is an eigenvalue if and only if there exists a non-zero vector V in the null space of T minus lambda times iv. But this is the same as telling that T minus iv is not injective. So, this is if and only if, which is if and only if T minus lambda iv is not injective. So, lambda is an eigenvalue of our given linear transformation T if and only if T minus iv is not injective or if T minus lambda iv is not invertible. So, that is an alternate definition we can keep to check whether something is an eigenvalue. This is at times useful. For example, let us consider one of the examples we already looked into. Let us maybe consider the first example that might be so I have not put a number, let me put a number here. So, recall that the first example was T of xy equal to 2x comma 3y. So, let us come back to this example. So, consider example 1 again revisited. So, T of x comma y is equal to 2x comma 3y. So, we know that both 2 and 3 are eigenvalues of T, and that is quite straightforward because consider T minus 2 times, so this is where T is from R2 to R2. So, T of consider T minus 2 times IV, and we would like to see whether its eigenspace or rather its null space is just the 0 vector or there are more. But we already know that if you consider T minus 2 IV of say x comma y, this is just going to be equal to 0 comma 3y, right? And clearly the x axis or the subspace, let me put it like this, thus the subspace y equal to 0, which is a one dimensional subspace, is contained in the null space. Write it here, n of t minus 2iv. Similarly, x is equal to 0 is contained in the null space of t minus 3 times the identity map. So, yes, this also tells us that 2 and 3 are eigenvalues. This also tells us that t does not have any other eigenvalue. So, why is that the case? Because consider t minus lambda iv. Let me just leave it as an exercise for you to check that t minus lambda iv is invertible. For all lambda which is not equal to 2 or 3, and therefore it cannot be not injective. It has to be therefore injective because it is invertible, and therefore the null space of t minus lambda I will just have the 0 vector, and therefore it cannot be a eigenvalue. Okay. Okay, next let us discuss the relationship between diagonal matrices and eigenvectors. So, we have already seen that if we have a diagonal matrix, the coordinate bases turn out to be eigenvectors, or in other words the matrix of the linear transformation corresponding to it is a diagonal matrix, right. So, let us make it more formal here. So, let us put it into a theorem or maybe a proposition. This proposition states that a linear operator on a vector space V is having a diagonal matrix if we have a basis which consists of eigenvectors. So, let us start with linear map from V to itself. So, let T from V to V be a linear transform, is a linear operator on V which is of dimension n, let us say, which has dimension, which has finite dimension. Let us say n. Then if V1 to Vn is an ordered basis of V, consisting of eigenvectors of T, so let us call it beta. Beta equal to V1, V2 up to Vn be an ordered basis of V consisting of eigenvectors of T, then, so let us remove this then. What do we have as a conclusion? Then the matrix of T with respect to the basis beta will be a diagonal matrix. Then the matrix of T with respect to beta is a diagonal matrix. The converse is also true. Let me write it down. Conversely, if the matrix of a linear transformation corresponding to a basis beta is diagonal, then the basis vectors in beta are eigenvectors of T. Conversely, if the matrix of linear transformation, the matrix of T, so if T beta is a diagonal matrix, corresponding to an ordered basis beta, which is say V1 to Vn, then Vi are eigenvectors of T. So, the proposition tells us that if we have a linear operator with a basis of eigenvectors of T, then with respect to this basis, the matrix of the linear transformation will be a diagonal matrix. In fact, we will see that the matrix will have as its diagonal entries the eigenvalues. And converse is also true, that if you have a matrix which has a diagonal, which is a diagonal matrix with respect to some basis, then the vectors in the basis will be eigenvectors of T. Let us give a quick proof of this. It is going to be actually quite short. So, let us see what the first statement says. This first statement says that we have a basis consisting of eigenvectors of V. So, given we have a basis beta, which is say V1 to Vn, consisting of eigenvectors of T. Let us see what is the matrix of T with respect to beta, but to do that we have to look at what is T of Vj, right. So, what is T of Vj? T of Vj is some lambda j times Vj, right, where lambda j is the eigenvalue of Vj. Remember that each of the Vj's are eigenvectors of T. So, what does that mean? This implies that Tvj beta is just equal to 0 0, there is a lambda j in the jth column, 0 dot 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 0, right, where lambda j is in the jth row. But Tvj beta will just turn out to be the jth column of the matrix of T, and piecing this together, we have T beta beta will just turn out to be the diagonal matrix of lambda 1, lambda 2 up to lambda n, where lambda I is the eigenvalue of the eigenvector Vj. Let us next prove the converse to this proposition. The converse is telling us that if we have a diagonal matrix, so let beta be beta equal to V1 to Vn be a basis such that T beta is a diagonal matrix, be a basis such that we just actually go back in the previous argument and we get it is equal to say diagonal of lambda 1 to lambda n. But what does that mean? By very definition, this just implies, let me leave it for you to check, that T Vj is then equal to lambda j Vj for j equal to 1 to n. This just tells us that V1 to Vn are eigenvectors corresponding to lambda j. Alright, so we have proved the result. So, we have observed that any linear transformation, if it has a matrix which is diagonal, then there is a basis consisting of the eigenvectors, and the vice versa. If there is a basis consisting of eigenvectors of our given linear transformation T, the matrix is also a diagonal matrix. So, this motivates a definition of that of diagonalizability. So, we say that a linear transformation is diagonalizable if we can get hold of a basis with respect to which the matrix of T is a diagonal matrix. So, let us give a definition. we say that a matrix, we say that a linear transformation T from V to itself is diagonalizable if there exists a basis beta with respect, let me write it such that the matrix T beta beta is a diagonal matrix. So, one of the most straightforward examples is the linear transformation corresponding to a diagonal matrix. They have to be diagonalizable, right. So, example, in fact example 1 is diagonalizable, T from R2 to R2 such that T of x comma y is equal to say 2x and 3y. This is diagonalizable by the very definition. Why? Because what will be our beta here? Our beta will just turn out to be the standard basis. In fact, let's start with a diagonal matrix. So, let A equal to diagonal of A1 to AN be a diagonal matrix. Then LA is diagonalizable again with respect to the standard basis of Rn. It is an n cross n matrix which is a diagonal matrix, right. So, with respect to the standard basis, the matrix of LA is a diagonal matrix, and by definition this is going to be a diagonalizable linear transformation. Okay, so let us look at one more example we had considered. Let us revisit one of the examples which we had promised to revisit, which is this example 4, which is basically the reflection along the line joining 0 to 4 3. So, let me write it down. So, let us consider, let us revisit example 4. What was our T? T was a map from R2 to itself given by reflection along L, which is the line joining the origin to 4 comma 3. Let me not write 2, which is the origin line joining 0 and 4 comma 3. It is an infinite line. So, we do not want to consider the segment, it is a line and you reflect every vector along this particular line. So, we had noticed that we had 2 eigenvectors for this linear map T. So, also recall that 4 3, the vector 4 3 and 3 minus 4 are eigenvectors with eigenvalues 1 and minus 1 respectively. But we also know that or I will leave it as an exercise for you to check that 4 3 and 3 minus 4 are linearly independent. What can we say about a set of 2 vectors in R2 which are linearly independent? It should necessarily be a basis. So, let beta be equal to the set 4 3 and 3 minus 4. Let us try to see or let us just jump up to look at what we did prove as a proposition. We have obtained a basis of T which has eigenvectors and which has every vector as an eigenvector. So, this means that T with respect to beta is equal to 1 0 0 minus 1. So, this particular form is quite nice. So, this particular form is quite nice because if you now consider T square, what is going to be T square? If you notice, this is going to be again beta with respect to beta, this will just turn out to be the product of this matrix with itself, which is going to be the identity matrix, which is the identity matrix of the identity with respect to the basis beta. And hence, we have obtained hence the matrix, the linear transformation T when multiplied by with itself will give you back the identity. So, it is an inverse of itself, that is what we have just proved. So, right. So, if we can get hold of a basis which has eigenvectors, then it is quite useful, as you can notice. We can say a lot more than what meets the eye directly. All right. So, we have just defined what is meant by diagonalizable for a linear transformation. We would also like to do the same for a matrix. So, let A be an arbitrary n cross n matrix. So, let A be an n cross n matrix. So, we will say that A is diagonalizable if the corresponding linear transformation is diagonalizable. We say that A is diagonalizable if the linear transformation TA LA is diagonalizable. So, notice that A to begin with need not be a diagonal matrix, A could be some arbitrary matrix. And what is LA? LA is the linear transformation corresponding to A. So, if you look at the standard basis and look at the matrix of LA with respect to the standard basis, we will get back A, but A need not be a diagonal matrix to begin with. However, if you consider the linear transformation LA and if we could get hold of some basis of Rn with respect to which our linear transformation LA is a diagonal matrix, then we say that A is also diagonalizable, or then we say that A is diagonalizable. So, needless to say, examples, all diagonal matrices are already diagonalizable with respect to the standard basis. You look at the matrix of LA, all diagonal matrices are diagonalizable. Okay, let us now look at a necessary and sufficient condition on when we can say that a matrix is diagonalizable. That is captured in the next proposition. So, proposition. So, let A be an n cross n matrix then A is diagonalizable if and only if we can get hold of a diagonal matrix D and an invertible matrix Q such that A is QD Q inverse. If and only if there exists a diagonal matrix D and an invertible matrix Q such that A is equal to QD Q inverse. So, notice that A is equal to QD Q inverse tells us that A is similar to D, but D is a diagonal matrix. So, this is rephrasing. An n cross n matrix is diagonalizable if and only if it is similar to a diagonal matrix. Diagonalizable if and only if A is similar. Recall the definition of similar. We say that two matrices are similar, A and B are similar if A is equal to something like QB Q inverse, where Q is some invertible matrix. So, A is similar to a diagonal matrix. So, this is a good characterization to keep in mind. So, let us give a proof of this proposition. So, suppose A is diagonalizable. Oh, I have already stated the proposition, sorry, I was writing proof. So, let us look at a proof of this statement. So, we have already assumed, let us assume that A is diagonalizable. So, let us assume that A is diagonalizable. What does that mean? That means that the matrix LA, that matrix is diagonal with respect to some basis. So let beta equal to say V1 to Vn be a basis. Let me call it beta prime. Beta, let us keep it for the standard basis. So, let beta prime be a basis of Rn such that La beta prime is equal to a diagonal matrix. So, let us say this is diagonal of A1 to An. Let us call this D. So, we have assumed that A is diagonalizable. By definition, LA is diagonal, is a diagonal matrix, or LA is a linear transformation which has a diagonal matrix with respect to some basis. Let us call that beta prime. So, with respect to beta prime, LA has the matrix representation given by D. But then what is LA? LA is just I composed with LA composed with I, where I is the identity matrix. So, LA is just IV LA IV, or where V IV is the, so let me just drop the IRN, this is where IRN is the identity matrix. Sorry, identity linear transformation in Rn. And now let us look at the basis, the matrix of LA with respect to beta. LA beta beta, where beta is the standard basis. This is equal to A. Let beta be the standard basis, and hence by definition LA beta beta is nothing but A, but let us just write it now as LA or I LA I from beta to beta. Now let us write this to be equal to I LA I from beta to beta prime to beta prime, beta prime to beta, by the very definition of or by the consequence of how the matrices behave with respect to composition. Let us call Q to be the matrix. So, let Q be the matrix I beta prime beta. Then this is a change of basis matrix, then Q inverse is nothing but I beta beta prime. This is something which we have already seen, and therefore A is nothing but Q. What is the matrix of LA with respect to beta prime? Recall that beta prime was exactly that basis with respect to which LA was a diagonal matrix. So, this is QD, Q inverse, and that is precisely what we had set out to prove. Recall what we had written in the proposition. This is diagonalizable if there is a matrix which is diagonal D and an invertible matrix Q such that A is equal to QD Q inverse. Okay, now let us look at the converse. We have only shown one side of the proposition. So, to prove the converse, let A be equal to Q D Q inverse, where D is a diagonal matrix and Q is an invertible matrix. So, we also know that the fact that D is a diagonal matrix tells us that DEJ is lambda j Ej, where lambda j is the jth entry along the diagonal, right. So, what we will do is let us consider the following vectors: beta be equal to, so this is the standard basis. So, let beta be the standard basis Then what do we know about DEJ? By definition, DEJ is something like lambda j times EJ, where lambda j is obtained in the lambda 1 to lambda n, right. Okay, let us now consider beta prime, where beta prime is given by QE1 up to QEn, and let us notice how beta prime, A behaves on beta prime. So, notice that dq inverse of QEj will just be equal to DEJ, which is equal to lambda Ej, right. So, what is going to be Q then? Q dq inverse of QEj is going to be Q of lambda Ej, but this is a linear map, this is going to be lambda times QEj. That means QEj is a eigenvector for QD Q inverse. QEj is an eigenvector of QD Q inverse. So, what do we have now? Beta prime is a set. So, recall that beta prime is a set consisting of eigenvectors of QD Q inverse. But let me put a claim down. This beta prime is a basis of Rn. If we prove this claim, then we are done, because then we would have obtained the basis of Rn, which consists exclusively of eigenvectors of our given matrix, right, or given linear transformation, whichever way you want to look at it. But then what is beta prime? Beta prime is the image of a basis under an invertible linear transformation. I leave this as an exercise for you to check at this time, that if you look at the image under an invertible linear transformation, then that will turn out to be a basis. So, let me just leave it as an exercise for you to check this part, and with this we have obtained a basis with respect to which the matrix of QDQ inverse is diagonal. Hence, QDQ inverse is diagonal matrix with respect to beta prime, which is the same as saying that A is diagonalizable. Okay. So, if we actually look at this proposition carefully, it is telling us that a given matrix is diagonalizable if and only if it is similar to a diagonal matrix. And the previous proposition was telling us that some linear transformation is diagonalizable if we can get hold of a basis consisting of eigenvectors, right. So, putting these together, we can explicitly say what our D and what our Q is going to be. So, let us just write down a proposition explicitly mentioning what our D and Qj are. So, proposition. So, let A be an n cross n matrix suppose V1 to Vn are vectors, or it is an ordered set. So, are vectors in Rn such that A Vj is equal to lambda j Vj, and such that they are linearly independent, and let us call it beta, and such that beta is linearly independent then A is equal to Q d Q inverse, where Q is the matrix obtained by inserting the vectors V1, V2 up to Vn, and D is the matrix obtained by putting in the corresponding eigenvalues. So, we can very explicitly compute the eigenvalue of Vj. Okay, let us give a proof of this. So, we have already done all the hard work. Let us just go back and see what we had noticed. We had noticed that we will get an equation of this type. We will get A is Q d Q inverse, where Q is I beta prime beta. Yeah, so let's just redo it. Let's recall that by or from the proof of the previous proposition. We have LA beta beta, which is our matrix A. This is equal to, what did we call this thing? Let us call this beta prime. The proposition, let us call the ordered basis to be beta prime. So, notice that this is linearly independent, forces it to be a basis because it is n linearly independent vectors in a vector space of dimension n. So, this will just turn out to be equal to LA beta prime beta, no, this will be I beta prime beta and I beta prime. But what is LA beta prime beta? LA beta prime beta is just beta prime is just diagonal of lambda 1 to lambda n, where lambda I are such that A Vj is equal to lambda j Vj, where lambda j are such that A Vj is equal to lambda j Vj. And what remains is to check for what is I beta prime beta. So, this is the change of basis matrix from beta prime to beta. So, what will be the jth column of this matrix? The jth column will be I of Vj, where Vj is the jth vector in the ordered basis beta prime. So, I of Vj is just equal to, in the jth column of this change of basis matrix. Let me write it again, let me write it afresh. The jth column of the change of basis matrix I beta prime beta is the column vector of Vj, and therefore I beta prime beta, which is, let us say, Q, is nothing but V1 to Vn. Okay, so in the next video, let us discuss techniques for computing the eigenvalues of a given linear transformation.